that worked pretty well. So, I said I was going to work on podcasting, and that's, I think, what I've got up and running today. All right, so I spoke to some people, what's the best way to do this, and they said to grab a mic, or at least buy a mic on Amazon. So you get like cheap USB mics to plug in, and so I did some research, I found the best one at a pretty decent price range, and had that requisition to be ordered. And so I got it in the mail, and what I received is this monstrosity. I thought that I was ordering a mic that was like yay big and would fit in my pocket. Instead, every time I show this to people, there are jokes about overcompensating, and I have no idea what that even means. So, this is our mic. Now, it's supposed to be, I have a feeling that the audio, it's gonna take some troubleshooting. I don't know how good the audio is gonna be on today's, but we'll at least have the video. So it might take us a week before I've really got this thing honed in with the correct settings and whatnot. But yeah, so we're officially podcasting now, and so the idea is that we'll record a video, and it will be in real time, and it will record my lecture. And let's see. I think as long as this little thing's blinking, I think we're recording. So, all right. My wife and I went out to dinner last night, and we were driving home, and we got to my house, or our house, and she was like, "Is there a bush growing in our yard? Like in the front yard?" We don't have a bush in the front yard. And I was like, I really don't think so, honey. And so as we got closer to the house, we went around, and we don't use the front entrance much, so we go around front, and my God, we are trashy people. It's our Christmas tree. We just threw it out the front door. We were like, we'll deal with it later. And there it still sits. The only thing missing is like a Trump sign, and I figured I stay pretty apolitical. I figured that was safe. So anyway, exams done. We don't have even homework due until after spring break, and so we can kind of sit back and relax and do some fun chemistry things from here on out. I usually save this talk till after the first exam. Those of you that have taken me before know that I put a lot of emphasis and improvement and your ability to achieve a high score on the final. And so, by the time we get to the end of class, if you're not happy with where your grade's sitting, keep in mind that I really like to see and I really take into account and consideration improvement over the course of the class. So, I don't like to promise things, but I don't really care what your grade. If you come into the final and you ace it, I'll give you a grade that's appropriate for that. And so just keep that in mind. One exam's not going to tank you. All right. So I got a new model kit. I also had the department order this for me, and so this is what I did yesterday for like 2 hours. I just played around and built things. Just really quickly, so an alkene, right? So now we've got our pi bonds, and so purple for pi bonds, right? And so what you find is if we try to rotate this thing, we're twisting our pi bond, and so ultimately that thing would break, and so that's why we don't have bond rotation, right? We're no longer going to have that parallel overlap of our p orbitals here, and so that's no good, and so that's why we have two different possible stereoisomers, both cis-trans or EZ, depending on the structures. All right. So we left off, we were on, I think we got through maybe rule 2 of the priority rules on Monday, is that right? I think so, we can, let me make sure I know where we're at. All right, so yeah, we had just looked at rule number 2. So let's review these really quickly. So we're talking about how we can name stereocenters to tell between molecules that have the same connectivity but different spatial orientation. And so what we've got to be able to do is when we've got lots of groups on there, we need to be able to rank them, and then we can use those numbers as information and use that as a guideline to name our stereoisomers. And so we said, well, the easiest way to do it is we're just going to look for a higher molecular weight. And so that's rule number 1. If your groups have a different molecular weight, the one that's heavier has the higher priority, or at least I should say atomic weight, because we're looking specifically at the atoms in question. And so here we've got a nitrogen, here we've got a carbon, and so nitrogen's bigger, it has the higher priority. On the other side we have an oxygen and a hydrogen, and so oxygen is higher priority. But of course we're going to run into cases where the first atom on each side are the same, right? So here it's easy on the right side. Bromine's obviously heavier than hydrogen, but on the left side we've got a carbon here and a carbon here, so that doesn't give us enough information. So then we talk about rule number 2, where we say, well, if number 1 doesn't work, basically we're just going to start looking for points of difference. We're going to start looking for the heaviest atom connected to that first atom, right? And so ultimately, rule number 2 can be relatively infinite. We can just keep counting away. If there's no difference in the second point of attachment, then we'll go on to the third point of attachment. And so here we can see we've got a carbon. The heaviest thing that this carbon is connected to is a what? It's a hydrogen, right? We don't count back this way. We're always going to count just the 3 things out. And so it's a hydrogen here. The heaviest thing this carbon's connected to is what? It's a carbon. And so our heaviest, or our first point of difference is going to be this carbon and then one of these hydrogens up here. And so that way, again, we just follow atomic weight. We know that this is heavier. And so that's going to be number 1. All right, so that's pretty much the rules. There is going to be one additional rule we need to consider. And so that's going to be what happens when we run into systems with pi bonds. So what we'll say is that pi bonds count as copies of bonded atoms. Hopefully this mic will do a good job of picking me up as I walk. I know, I meander when I lecture sometimes, so hopefully it'll do it. And I mean, it's supposed to be really good at picking up audio, so if there's questions and things, today I'll probably repeat them just to make sure they're on the mic, but I think they'll also pick you up, so if you want to be heard, all you gotta do is speak up, I guess. All right, so pi bonds count as copies as bonded atoms, and so for example, we could have something that looks like this. So yet again, we'll just keep going with the double bond. I think that's the easiest way to do it. All right, so our connectivity will look something like this. All right, so on the left side, our first atom connected on the top is this carbon, and on the bottom side it's a hydrogen. And so which is the higher priority group? It's the carbon, so that's not too bad. So we've got priority 1, and then at the bottom we've got priority 2. But on the right side, let's remind ourselves what exactly is going on right here. So at the interface where we have a single bond drawn into a triple bond, how many carbons are there to the right if I cut it right here? There's 2, right? So we've got a carbon here. So this carbon's connected to a single bond with this carbon, and then a triple bond to this other carbon. So let's not forget that. And so what we've got is our first atom's a carbon, and down here, what's our first atom? Also a carbon, so no help. And so really what I like to do is I like to redraw this thing. And so the way that I'll redraw it, I'll come over here to the right side, and I think this makes it easier to see. So what we do is we say, well, this carbon right here, it's triple bonded to a carbon, and so we're just going to say it's connected to 3 carbons in terms of our priority rules. And so what we can do is we can redraw it out to look like this. So kind of have a more detailed picture of what we're looking at. So to the left, obviously, we've got something like this. So we've got that methyl group, and so our carbon's connected to 3 hydrogens. Now on the right, what we've got is more or less, let's see, we've got methyl, hydrogen. On the top side, well, what we've got really is something like that, but that's not going to help us in terms of our drawing. And so what we're going to do is we're just going to say, well, that carbon, we'll say is also right there. So basically now we can see, well, it's triple bonded, so it's more or less kind of bonded to 3 different carbons. And so what we do is we can just draw it out like this. And so ultimately, that triple bond, that carbon, goes there, and it goes there as well. And so now what we have is we have all the bonded atoms that we can start counting. And so when we count to the right, we've got our first point of attachment, that's a carbon, and that, again, is no help. So then we look at the highest second point of attachment. So down here, that would also be a carbon. Up here, we've got a carbon. All right, so what's our second highest point of attachment to this carbon? Carbon. Also another carbon. What about up here? Carbon. Also a carbon. All right, what's our third point of attachment? It's a hydrogen. What about up here? Carbon. It's another carbon. And so finally, we find that our first difference is going to be between this hydrogen and this carbon. And so what's the first priority?
The top one.
The top one, yeah. So We'll label that a 1. We'll label that a 2. And so when we name this thing E or Z, what are we going to call it? Yeah, we're going to call it Z because our higher priority groups are on the same side. We can't give it cis or trans because we have to have specific groups in question that we're talking about. And that wouldn't be enough information to clarify what our stereoisomer is. Yeah. Yeah, and so basically what we're looking at when we're trying to figure out the difference in our groups is back up here we can say, well, on this carbon, we look here, we see it's a carbon, we look here, we see it's a carbon, and so it's the same thing, right? So then we have to count one further atom away, and so we're going to have 3 possibilities for each group because each of those carbons is bonded to 3 things. So we just start at the heaviest and work our way down. So down here, our heaviest thing that this carbon's connected to is a carbon. Up here, the heaviest thing it's connected to is a hydrogen. And so since it's bonded to a carbon on the bottom, that's going to be the higher priority group. Yeah. Yeah?
If that group on the bottom had been like a dimethyl group instead of just a methyl group,
You're talking about right here?
would that mean the one on the bottom got a higher priority because it has more hydrogens than the one on top?
That's a good question. Let's take a look at what that would be. So she's asking what would happen more or less if we had a molecule that looks like this. So this is a dimethyl ethyl, like that. And we're just going to do the right side. And so we'd say that up top we've got carbon, carbon, carbon. And so let me also add, this carbon right here is also triple bonded to this carbon right here. And so what we can say is that also we're going to have 2 carbons off of that, just like that, right? So your carbon, both of those carbons are triple bonded to another carbon, right? And so we're just drawing those in. We're filling in kind of the blanks. All right, so each carbon's going to be connected to 3 things, and ultimately this is, or these 2 things come from the triple bond. All right, so what we've got is something that looks like that. And then for the dimethyl ethyl, so we've got our carbon connected to 3 carbons, which are then all methyl groups. So those are all CH3s. And so what we could do at this point, and we're getting down into some pretty deep territory where we're not going to spend a lot of time counting so far away from our carbons, but if we had to do this, we would look and we would say, well, this carbon's bound to 3 carbons, so is this carbon, and so we'll keep going away, and so basically these are equal, so we can just pick one, and so now this carbon's bound to 3 hydrogens, whereas this carbon is bound to at least 2 carbons, right? And so in this case, again, this would be the higher priority group. So you just kind of keep counting away and you look for the first point of difference, and then the point of difference with the heavier atom is going to be the higher priority. Yep. So that would be 1, and that would be 2. All right, so those are kind of the rules for prioritizing our groups, and for the most part, these are going to be simple. We're going to be comparing things like a bromine and an alcohol, and so clearly we know a bromine's heavier, and so we just want to be able to give that number 1 and the alcohol number 2. Yeah, Cynthia?
Are you still confused as to where the extra carbons come from?
Yep, so if we go back up here, this carbon right here, if we kind of pretend that we're disconnecting it, this carbon is connected to 3 things, right? Each of those 3 things is a carbon, right? Because it's triple bonded to the carbon. And so we count, in terms of our priority rules, those 3 bonds involved in the triple bond both count as a carbon that it is attached to. And so when we redraw it, we say, well, it's connected to, in the sigma bond, but then there's also 2 pi bonds from the triple bond, right? And so that's where those carbons come from. It's just saying, well, it's bonded to 3 or at least 1 carbon 3 times, and so we just say 1 times 3, right? And so it's connected to 3 carbons. Yep. All right. So that is how we're going to prioritize our groups, and so now we're going to have some conversation, or a conversation about chirality. And so our theme song of the day was Mirror, and so very much a big part of chirality is this idea that molecules are going to look differently, basically through a mirror. All right, so this is going to be section number 3. We will title it Chirality. And so what we'll say is, for part A, we're going to say that there's two types of objects. So, at least in terms of our classification here. So there's two types of objects. When it comes to chirality. So the first kind, we're going to call achiral. Alright, so achiral, just like chiral, but with an A in front. And so what that means is that an achiral object is going to be an object that is superimposable on its mirror image. And so another way of saying that is it would be an object that is identical to its mirror image. Basically, there's going to have to be some sort of symmetry in this object. It's not just molecules, it's objects in our daily lives. There's going to be some form of symmetry that allows the mirror image of our object to be the same, basically, as the object itself. All right, so what that does to be an achiral compound or molecule or object in life is that it's going to require symmetry. All right, so our molecule requires symmetry, and so what I've decided to do to kind of show this is, so here's an object. All right, so I mean for this to be as symmetrical as possible, so maybe we'll be a little more careful when we draw. Okay, so there's Mr. Smiley. He gets a name. All right, so Mr. Smiley is there, and he's checking himself before he goes out each morning to work, and so he looks in the mirror. All right, so there's our mirror. All right, so the mirror is in this y-axis, and so what that means is that when you look in a mirror, your right hand in your mirror image becomes what? Becomes your left hand, and so that's what Mr. Smiley sees. So his right ear becomes his left ear, and so when he looks in the mirror, what he sees ultimately is a picture that looks like this. All right, now if I were a better artist and I copied one of these pictures and then overlaid it on top of the first one, would they line up perfectly? They should, right? Because Mr. Smiley is also a beautiful man. He's perfectly symmetrical. And so, in fact, his mirror image is completely identical to the actual object, or to his actual face. And so, bam, this thing is identical. And so, by definition, if we have an object that is superimposable on its mirror image or is identical to its mirror image, it is achiral. And it's achiral because Mr. Smiley has this perfect plane of symmetry right down the middle of his face, like that. Beautiful man. All right, so this also exists in the chemistry world, and so what I've got is, with my models, I've got an example of an achiral molecule. Okay, so basically, this molecule, let's see, let's put it like this, and so we're going to put it in the mirror, and so what's going to happen is its right side is, or its left side is going to become its right side and vice versa, right? And so what we end up looking with is something that looks like that. Now, when you look through the mirror, your nose, is it still your nose or is it on the back of your head? It's still your nose, and so something on a wedge is going to stay on a wedge, just like you can see your nose in a mirror. And so this red thing that's on a wedge, as you're looking at it, it's on a wedge over here. It's just on the opposite side. Same thing for the green. It's on a dash. The back of your head does, I mean, you can't see it if you look through a mirror, right? And so it stays the back of your head. So the green's on a dash, and this green's on a dash too. And so what we've got here are mirror images of each other. Are they identical molecules? Are these identical molecules?
Yes. There we go. Yes.
All right. Here's a big key point when it comes to compounds. If we're ever going to have chirality in a molecule, we've got to have 4 different groups. I mentioned this last time. Do we have 4 different groups here? No, we have 2 blue groups, right? 2 of these groups are identical, and because they're identical, the mirror image, we can simply just rotate this thing and we'll be able to basically superimpose it. So despite the fact that this... Let's make sure we do. Takes a little practice. All right, so these are mirror images, but certainly what we can do is rotate this enough such that ultimately those are the same molecule, right? Everybody see that? I'll have these models up here after class. If you want to come up and rotate and play around with them, be my guest. All right, so in terms of a molecule, if we draw that out, what we end up with is, say, let's put a bromine there. We'll put methyls on wedges and dashes. And we'll put a fluorine there. And so if we do the same thing with our molecules we did with Mr. Smiley, what we're going to have is, well, the things on our right side, our methyl groups, they're now on our left side, but they keep the same depth, right? The nose is still the nose and vice versa. And so I guess in this case it doesn't really matter because they're both methyl groups, so we'll draw it out to look like this. All right, so that's the mirror image. And so what we've seen with our models up here is when we have a case where two of those groups are the same, do we have a chiral or an achiral molecule? It is definitely achiral, and again, it's because these things are identical. The mirror image does not change the molecule whatsoever. Josh?
So pictorially, the molecules are flipped, but in actual space, if you were to put it in like a 3D space,
yeah, because
everything's the same.
Yeah, all you've got to do is if you wanted to take this right molecule and see that it's just like the left molecule, if you had a model, you would say, you basically take this fluorine, you would rotate all these three things on the bottom, right? So you would take this fluorine, you would rotate it around the back to there, and then these methyls would rotate around to here, and you'd see that, in fact, that is the same exact molecule. All right, so just like we can do with our model, yeah? Yeah?
You mentioned this is only the case of two that are the same.
So anytime, really it's going to be the case anytime that they're not all different. So if we have two that are the same, it's achiral. If we've got three are the same, achiral. Four are the same, achiral. You're always going to have the same molecule in that case. All right, so we're looking through our mirror and seeing that when there's symmetry in a molecule, what we've got is an achiral identical compound. All right, so that means we're also going to have number 2 here, and so for number 2, if we're not talking about achiral things anymore, we're talking about what? Chiral things. All right, so we're going to talk about chiral molecules here. Did I tell you, did I hear you guys said I love this thing because of the light? I just realized that I can basically have a desk lamp up here. Okay, so a chiral object is basically the opposite of an achiral object. And so we say that a chiral object is one, an object that is not identical to its mirror image. All right, so an identical that is not, an object that is not identical, and so let's bring Mr. Smiley back into play. Question? Okay. So, and additionally, I'm going to add to that, I'll say that most objects are chiral. All right, so unlike Mr. Smiley, I'm not a beautiful man, and so when I look in the when I look in the mirror, I clearly do not have a nice plane of symmetry down my face, and so I am a chiral thing. If you took my mirror image, it would not be the same thing. It would be an opposite-looking thing of me. And so, for example, Mr. Smiley, he decides that he wants to see what it's like for the normal people. And so what he does is he winks. He winks in the mirror. Mr. Smiley, you crazy, crazy man. All right, and so Mr. Smiley winks in the mirror, and of course, now do we have that beautiful plane of symmetry right down his face? He's still beautiful, absolutely. But we don't have the plane of symmetry because what he sees in the mirror is, again, the things on the left become the things on the right. And so he was winking with his left eye in this picture. Of course, what does he see in the mirror? And he's now winking with his right eye, like that. All right, and so these two images, assuming that it's not just a, this 2D picture, let's say that Mr. Smiley's head has depth, so we can't just flip this over. Are these the same images? No. Mr. Smiley is no longer looking at the same exact thing, and no matter what we do to this, we're never going to be able to superimpose these two things. So, Mr. Smiley, when he winks, is he chiral or is he achiral?
He's chiral.
He is now chiral. He quickly unwinks so that he can return to being beautiful. All right, so it is chiral because these mirror images are not identical. We've lost our plane of symmetry by him winking his left eye. So of course we're going to be doing this probably with molecules more than we're doing it with my poor crude drawings. And so what we can do is we'll take something. All right, so is this thing connected to 4 different groups? Yes. It is. All right, so I brought silver into the mix. And so what we've got here is we can go ahead and try to find the mirror image. All right, so what we got is the things on the left become the things on the right. So silver on the left becomes silver on the right. Wedges and dashes don't change because that's depth, and so that's our nose, and it's still in front. So red is on a wedge to your right, now it's on a wedge to your left, and so blue makes sense too. But what happens when we try to overlay these two things? All right, so we can match up our green and our silver, but what's wrong? Red and blue are no good. All right, so let's try to fix red and blue. So let's match up our red and blue. What's going on with our green and our silver? They're flipped. No matter what we do, because there are 4 different groups, these are actually 2 different molecules, and it's because there's just no way that we'll ever be able to overlap them. They are chiral molecules, and so importantly, what we always want to remember is that a chiral molecule is going to have 4 different groups, and so our example will be, let's say we change one of our methyl groups from above into an alcohol, and so instead of having 2 different groups, or at least 2 of the same groups, now they're all different. And so when we draw our mirror, our bromine's still on top, but our alcohol, which was on a wedge to the right, is now going to be on a wedge to the left. And then our methyl group, which is on a dash to the back, I'm sorry, a dash to the right, is now a dash on the left, and then fluorine is on the other side. And so we look at this, we look at this carbon, we say, well, it's got 4 different groups, and so is it chiral or achiral? It is a chiral molecule, which means how many possibilities are there for the way this thing's bonded together? How many different molecules are there? There's 2, right? And we're going to learn, so we'll talk about that in a minute, why there's only 2. Okay, so we would point at this carbon, and what we would do is we would call that a chiral center. So chiral centers are incredibly important, especially medicinally, because again, we as life forms, are we chiral or achiral at a molecular level? Chiral. We are chiral because we have only one form, one handedness of the amino acids, and so our proteins only have that handedness, not the other handedness. Josh?
So to be achiral, you need to have less than 4 different groups.
Yeah. All right, so that's a chiral center, and these are not identical. So what we've got is the possibility for stereoisomerism. All right, so let's talk more about these chiral centers or stereocenters. So we'll go into part B. So part B we will label stereocenter, or aka chiral center. Now, it's not always carbon, because we've certainly seen cases where other atoms can be bonded to 4 different things that are different. So what about a nitrogen? Can a nitrogen ever be bonded to 4 different things? Yeah. Sure. What kind of charge does it have? It's got a positive charge, but still, it's possible. But in the vast majority of cases, what we're talking about are carbons, and so that's really what we're going to focus in on as we go. So we'll say that a stereocenter, or a chiral center, is typically, but not always, going to involve an sp3 hybridized carbon connected to 4 different groups. All right, and so for example, let's say that we've got 1 carbon here. Up top, we'll draw this group. What do we call that group if we were naming it? Starts with a P. You really are going to want to call it a benzyl or something. It's actually a phenyl. All right, and so just as we go down the road, whenever we're just talking about that 6-member ring attached to something, it is a phenyl substituent. If it's on its own, what do we call it? It's benzene. But when it's attached to something and we're describing it as a substituent, we call it a phenyl group. A benzyl group is actually, when referred to as a substituent, it is actually that. All right, so that's a little confusing. It's just something you need to memorize. So this is referred to as a benzyl group, but when we're just talking about the 6-membered ring as a substituent, it is a phenyl group. Okay.
Which is the phenyl group, the ring or the carbon attached to it?
The phenyl group is basically everything from our point of attachment up, right? So where I've split it with the red line. All right, so in this molecule, we'll put a hydrogen here. We'll put an ethyl group here. And so as we get further into drawing these structures, what I might start doing is instead of drawing out CH2, CH3, we can even go further with our shorthand, and I could just call that an ET, which would stand for ethyl. And so we know what an ethyl group is, and so that's how we can even further reduce the complexity of our drawings. All right, so likewise, we can put a methyl here, and so if I wanted to be even shorter, what would I write? Yeah, I'd write Me for methyl. All right, so that's if you ever see that, don't be confused. It's just indicating the length of our chain. Okay, so we have 4 different groups. Our 4 different groups attached to our carbon. Just a quick yes or no. Yes. Yes, they most certainly are. We've got a methyl, an ethyl, a phenyl, and a hydrogen. Okay, and so what we can do is if we wanted to prioritize, all right, so what's going to always be our lowest priority substituent here? Hydrogen. Hydrogen is, if you see a hydrogen on a chiral center, you pretty much know it's number 4, and you're going to find that number 4 sort of has a special role as we start naming these things. What would be number 1? It would be phenyl, yeah? And that's because that carbon right here, we consider connected to how many carbons? At the first point of attachment. Going right, we've got 1 carbon there. Going left, we've got it double bonded to a carbon, which counts as 2, and so we consider that connected to 3 carbons, which is certainly going to trump our ethyl group, where this carbon is connected to 1, or down here, the methyl group, where the carbon is just connected to hydrogens. All right, so if the phenyl is the highest priority, what's number 2? Yeah, that's our ethyl. And so then finally, we put in our methyl for number 3. Okay, so if we draw the mirror image of this, and so does it matter how I orient the double bonds? No, because ultimately those double bonds are in a resonance structure where it's 50% single bond, 50% double bond. So it doesn't matter how we orient those double bonds. And so our hydrogen, which is on our left, is now on our right. And then our ethyl, which was going forward, is still going forward, except now on our left side. And then, of course, our methyl, that was on a dash, is still on a dash. Okay, does it matter that I've got the dash kind of more in our downward trajectory and then our wedge on the more downward trajectory there? No, because all the wedge and dash are saying is one's going forward and one's going backwards. And so it doesn't make any difference how you orient your wedges and dashes. You're saying the same piece of information. And so if we renumber again, we'd say, well, phenyl, of course, is still number 1. Ethyl is still number 2. Methyl is still number 3. And then our hydrogen is still number 4. And so what we've got here, what we always want to make sure is that when we talk about these 2 different molecules, are they the same molecule or are they different molecules? They're absolutely different molecules. And they're different molecules because they are not superimposable. They're bound to 4 different groups, and because they are mirror images of each other, they are not identical, and we can never overlap them. Yeah?
Sorry, I'm having trouble seeing. Okay, I guess it's difficult for me to see the mirror image. On the left there, I guess I'm sorry, my brain wants to switch those two, just because the dash and the wedge line, because it looks like they're.
Yeah, and you can do that. Okay. It's fine. It doesn't matter how you orient the wedges or dashes whatsoever. Yeah.
So when you flip it, you just have to make sure that whatever was the dash is still the dash.
Exactly. So when we go from one handedness to the other, or at least when we do the mirror image like this, we just want to make sure the thing that was on a wedge is still on a wedge, and the thing that was on a dash is still on a dash. Yep. Yep. Okay, so we've got different molecules, and this is going to bring us to something I really want to highlight, because we're going to get into some names. We're going to talk about relationships between molecules. So we'll talk about stereoisomers, we'll talk about enantiomers, we'll talk about diastereomers, and these words are really long and they sound really complicated, but we're going to boil them down to just the most simple definitions that we can. And so, we're going to start this. This is going to be a big deal. We're going to talk really briefly about enantiomers. And so the definition of enantiomers is that they are non-superimposable mirror images of each other. And because they're non-superimposable, are they the same object or are they different objects? They are different objects, very much so. So what we're always going to have when we talk about enantiomers, we're going to talk about two different objects. Which leads us to another idea about enantiomers, and that idea, and this is how I best remember what enantiomers are, and this is how I would like you to always keep in your head when we think about enantiomers. They are a very special pair. They always come in pairs, right? Because they are mirror images of each other. And so when we have cases where there are, say, 4 possible stereoisomers or 8 possible stereoisomers, enantiomers, as we describe them, if we take molecule A and molecule B, they're only enantiomers if they are mirror images of each other, and furthermore, there's only going to be that pair together. We can have other pairs, but they always are in groups of 2. All right, so enantiomers are a very special pair where we have objects that have the same connectivity, but they are non-superimposable mirror images of each other. And so, importantly, they have identical chemical and physical properties. Which should make sense, right? So if we have this molecule here, and then we have this molecule here, and of course their physical properties. Let's think about boiling point. All right, so boiling point is dependent on what idea? So intermolecular forces, right? And so because these are essentially the same thing, they're going to have the same intermolecular forces and thus the same melting point, the same boiling point. And so what that means is when they're together, they're very tough to separate because they're going to boil at the same temperature. All right, so enantiomers, a very special pair. They're non-superimposable. They are different objects, and they have identical chemical and physical properties because other than being reverse of each other, they're the same exact thing, right? Okay, so if you look through a mirror, you can tell that it's you, right? And pretty much when we talk about intermolecular forces, it's the same way. When it interacts with other things in the world, it pretty much registers it as the same object. Unless that environment is chiral, right? Like our body where it's a chiral environment and it has a right-handed or a left-handed glove, then it matters. But just out in the world, doesn't make a difference. Okay. So enantiomers. Let's talk about how we're going to classify chiral centers and tell the difference between enantiomers. So we'll write how to classify stereocenters or chiral centers. And so we've already said, what letters do we use to identify chiral centers? R and S. When do we use E and Z? It's for double bonds. So we use E and Z for double bonds. When we're talking about chiral centers, we're talking about R and S. There's 2 ways to do this. It's going to be necessary to be able to basically look at a stereocenter and determine if it's R and S. And so let's say that number 1, we want to prioritize substituents. Okay, so if we prioritize substituents, once we've done so, we can more or less put our group number 4 in the back. And so what I mean by that is if you're looking at your 4 or your 3D shape here. Let's say that silver is our lowest priority group. As you're looking at it, it just goes in the back. You no longer see it, such that you basically got a will of these 3 substituents, right? And so if you look at that, well, is that will oriented the same? No, these are enantiomers, right? And so if we just go alphabetically, blue, green, red, are we going clockwise or counterclockwise? In this case, we're going clockwise over here. If we go blue, green, red, are we going clockwise or counterclockwise? And that's basically how we are going to tell the difference between our 2 molecules. So we'll prioritize, we'll stick 4 in the back, and then we look at the 3 and we determine if they're going clockwise or counterclockwise. Of course, instead of alphabetically, we do it based on the priority numbers that we've given the substituents. All right, so let's see. I drew a different molecule than in my notes. So what we're going to do is, let's say we're going to look at this molecule on the left. And so since group number 4 is in the back there, or at least should be in the back, we're going to view it from this direction. All right, so everyone see how if we put our eyeball there and look at that molecule, now hydrogen is hidden in the back behind the carbon? All right, so that's what we're doing. And so if that's the case, that phenyl group, is that going to be, what direction would that be? It should be straight up. So I'm going to copy paste this down. I don't have to keep going back up. So copy, paste. Let's not go quite that way. Okay, so here are our molecules, and so if we were kind of going to draw a half Newman of this, we would say, well, we've got our carbon in the middle. And so our 4 is in the back, and we don't even see it. And so from our green eyeball right here, we've got our phenyl to the top. And from this perspective, our ethyl group, which is on a wedge, is that going to be to the bottom left or the bottom right? Bottom left, yep. And so that's where we'll put it. And then our methyl group on a dash is to the bottom right, because we're kind of looking at it from this direction, and so since it's on a dash going back into the board, you can see that it is on my right. Okay, so that is where our methyl group goes, and so we've prioritized these already. We've said that this is 1, our ethyl group is 2, and our methyl group is 3. All right, so if we're trying to classify what direction we would count 1, 2, 3, we'd say, well, that is 1, 2, 3. Is that clockwise or counterclockwise? That is counterclockwise, and so what we can say is that if it is counterclockwise, we give it S. All right, so that is the S enantiomer of this molecule, and it's S because we've taken that 4th substituent, we've hidden it in the back, and then we find when we count 1, 2, 3 on our substituents, it is counterclockwise. It is the S substituent. All right, so we can also do it for the right substituent. And so when we do so, again, we're going to put our substituent number 4, our hydrogen, in the back. And so that's why if you find a hydrogen on a chiral center, you already kind of know where to look, right? You just want to look in the direction that hides the hydrogen, more or less. And so if we want to hide the hydrogen, our eyeball, we'll look at our carbon from that perspective. So if we look at it from that perspective, again, our carbon's in the middle. Our phenyl hasn't changed. It's still just straight up. But now, our ethyl group, when we look at it from this direction, it's on a wedge. Is that towards you or away from you? It's towards you, and so if I look at it from that eyeball, is that on my right or my left?
Right.
Here I am, looking down this direction. All right, so what direction do I have to look at to see you?
Right.
I look in my right direction, right? We know our substituent is on a wedge. It's towards you, and so which side is that of mine is that on? Right. It is on my right side, and so that's how that eyeball sees it. All right, so we've got an ethyl on the right side. And then, of course, since the methyl is on a dash, that's going away from you. And so if I'm looking from the same perspective of my eyeball, that's on my left, because things going away from you are over here. I have to turn to the left to see those. And so that's where our methyl is. All right, so knowing our priorities, those haven't changed. We've got 1, 2, 3. So what we can do is we can count 1, 2, 3. We see that that is now flipped. So instead of going counterclockwise, we're now going clockwise. And so we would call this the R enantiomer of this molecule. And so when I talked about albuterol on Monday, I called one form R-albuterol and one form S-albuterol. So what that is that chiral center in albuterol, this same process was undertaken, and so we're able to classify the different kinds of albuterol in that way. Okay, so that's one way that we can go about doing it. Honestly, there's also this really cool trick with your hand that might make it a little bit easier. Okay, so this is how we would do it on paper. We can also use our hand. And so let's say, or we can take number 1 and we will say that we assign our thumb to 4. And so then what we'll do is we'll close our fingers such that they close 1 to 2 to 3. All right, so what does that mean? All right, so let's do it alphabetically. Again, we'll say silver is our lowest priority. And so if we're going to count blue, green, red, and I'm just making that up because it's the alphabetization of our groups here. If I put my thumb back, I have my fingers, and now my fingers, they can curl this way, but can they curl the other way? Without breaking them? No, they can't. And so my fingers curl one direction, and so if my thumb is pointed back in the direction of my hydrogen, and I curl my right hand, blue, green, red. Does my hand follow that alphabetization? It does. And so anytime that works, and it is your right hand, and this is the awesome thing about this, guess if it's R or S? It's R. All right, so if we close our fingers and we find that it's our right hand, what we have is the R enantiomer. Make sure I do this. All right, so that's the other one. And then likewise, all right, let's see if this works on this one. All right, so I'll try my right hand again. Silver's number 4. Point my thumb towards silver, and we want to go blue, green, red. Can I go blue, green, red with that hand? When I try to do that, what happens is it goes blue, red, green, and so it must be the other enantiomer. So of course, we point our thumb, now of our left hand, back to substituent number 4. And so can we curl our fingers blue? Wait a minute. Can we curl our fingers blue, green, red? Yes. We can now with our left hand. And so if it's our left hand, guess what it is? It is S. All right. I still use that in my day-to-day life if I need to classify whether things are R or S. And so what you can do is you can get the habit of just pointing your thumb towards number 4 and figuring out which way does this thing go, right or left. Okay. We're a little ahead in this section, so we'll just call it a day right here. Have a great weekend, and I will see you Monday.
Where's your office again? I'm coming in at noon.
10:59. Yep.
In here?
No, so I'm in ISC 1059, so do you know where the undergrad labs are?
This building.
Yeah. So it's
yeah, I can find it. So make sure it's 1059 this building.
Yes, sorry.
They shove people places.
Yep. Want your car?
Sure, baby.
Let's see. I'll text you. Probably similar 4-ish sort of thing. Maybe earlier. We'll see. See how it goes. Yeah.
Professor, I know you're still trying to work out the bugs with this.
Yeah.
I obviously record the lecture as well. I sync it to my computer every day, so if you find that you're not happy with the quality, mine's always high quality, crystal clear.
Okay.
I can send it to you, and you can just plug it right into yours if you need it. So
Thanks. Yep,
have a good
appreciate
weekend,
it.
Professor.
You too. Hey. Yeah, and it is a confusing thing. It seems like we could call it a pencil when we have this group here. Okay. So what we've got here in this group.
First, how do we know? Is that one of those common names we're supposed to memorize?
It is not a common name. It is that is the official IUPAC name.
Okay. Oh, right. Okay. Yeah.
Yeah.
And then, so
it different from the?
Basically, the difference is here, our connectivity is just the 6-membered ring. Here, we have a methyl, a CH2, in between our point of connection and our phenyl ring.
Okay.
So it's just a totally confusing thing.
What if you had like a propyl and then a 6-membered ring?
And so that'd be a different group. So a benzyl is specifically when we have just a CH2 in between our point of attachment and then our 6-membered ring.
Okay, and the phenyl is when you have nothing.
Just the 6-membered.
Just the ring. Okay, cool. Thanks.
Yep.